Welcome to our latest video on carboxylic acids, chemical reactions. This video is suitable for A-level students. By the end of this video lesson, you should be able to describe the chemical reactions that carboxylic acids have with alkalis, bases, metals and metal carbonates. You should understand that carboxylic acids can be reduced to form primary alcohols and undergo decarboxylation reactions to form alkanes with one less carbon atom. And finally, you should be able to explain how carboxylic acids can be converted into acid chlorides and esters. Now, in our previous videos on carboxylic acids, we've learnt that they have a COOH functional group. And remember, the functional group is the part of the molecule that determines its chemical reactions. And examples of carboxylic acids include ethanoic acid, which has a CH3 attached to a C double bond OH, and methanoic acid, which is produced by ants, which is HCOOH, and lactic acid, a more complex carboxylic acid, which has a CH3 attached to a COH, H, and C double bond OOH, and this is produced when milk ferments and in muscles when exercising. Now, carboxylic acids are weak acids, and weak acids are substances that partially split up into H+ ions when you put them in water. And the following equation shows what happens when you put ethanoic acid in water, because ethanoic acid will split up into ethanoate ions and hydrogen ions, and the process is reversible. And the acidity of a carboxylic acid depends on the stability of the negative ion, the anion, produced. And the less stable the anion is, the more likely H+ ions are to attack it and recombine with it, and the weaker the acid. Now, carboxylic acids are all relatively acidic because they can form a stable anion, where the negative charge spreads or delocalizes over the two oxygens and the carbon, and this makes it more stable and less likely to be attacked by H+, and less likely for the H+ to recombine with the ion and form the original acid. Now, the more stable these anions, the more H+ in solution and the more acidic the acid is. Now, carboxylic acids have typical reactions of acids. In other words, they react with alkalis, bases, metals, and metal carbonates to form salts. So, an acid plus base forms a salt and water, an acid plus alkali forms a salt and water, an acid plus metal forms a salt and hydrogen, and an acid plus metal carbonate or metal hydrogen carbonate forms a salt, carbon dioxide, and water. Now, we're going to look at the reactions of ethanoic acid, and the salts that are formed from ethanoic acid are ethanoate salts. And the ion for ethanoate is CH3COO-. Now, when writing the chemical formula for ethanoate salts or any salts from carboxylic acids, you write the organic formula bit first. So, for example, for sodium ethanoate, the ion for ethanoate is CH3COO-. The sodium ion's Na+. These ions have the same charge, so they cancel out. So the formula for sodium ethanoate is CH3COO-Na. And for magnesium ethanoate, we have CH3COO- for the ethanoate ion and Mg2+ for the magnesium ion. Now, I need two ethanoate ions to cancel out an Mg2+ ion, and therefore the chemical formula is CH3COO in brackets 2Mg. Now, it's worth pointing out that the chemical formula of carboxylic acid salts are often written with the charges of the ions still present in the formula. So for example, sodium ethanoate is often written as CH3COO- Na+. And this is to remind people of the ionic bond that's present between the two ions. So now let's test your understanding of this with some practice questions. So read through the questions, pause the video, have a go at them, and then we'll go for the answers. So question 1 is asking us to write word and chemical equations for the following reactions. So for 1A we have ethanoic acid reacting with sodium hydroxide. So we have an acid and an alkali reacting here. Now this is going to make a salt, sodium ethanoate, plus water. And the chemical formula for ethanoic acid is CH3COOH. Sodium hydroxide is NaOH. The salt, sodium ethanoate, is CH3COONA, and water is our other product, and that equation is balanced. Now for B we have ethanoic acid reacting with magnesium oxide, and magnesium oxide is a metal oxide and therefore a base. So acids and bases make salts and water. The name of the salt is going to be magnesium ethanoate, and our other product is water, and the chemical equation is going to be 2CH3COOH plus MgO, and that's going to make CH3COO in brackets 2 Mg plus H2O. And for C we have ethanoic acid reacting with a metal, calcium, so we're going to get a salt and hydrogen. The salt is going to be calcium ethanoate. So the chemical equation is going to be 2CH3COOH plus Ca goes to form CH3COO in brackets 2 Ca plus H2. So here are some more questions for you to have a go at. Once again, read through the questions, pause the video, have a go at them, and then we'll go for the answers. So for question 1D, we have ethanoic acid reacting with sodium carbonate and metal carbonate. So we get a salt, sodium ethanoate, plus carbon dioxide, plus water. And the chemical equation will be 2CH3COOH plus Na2CO3 forms 2CH3COONA plus CO2 plus H2O. And that equation is now balanced. Now for E, we have ethanoic acid reacting with a metal hydrogen carbonate, sodium hydrogen carbonate, and that will also form a salt, carbon dioxide and water, and we'll once again get sodium ethanoate as a salt. So we have CH3COOH plus NaHCO3 forms CH3COONA plus CO2 plus H2O. And this equation is balanced. And for question 2, you're asked to describe how the reactions of carboxylic acids and metal carbonates or metal hydrogen carbonates can be used as a chemical test for a carboxylic acid. And this is because when you add a metal carbonate or metal hydrogen carbonate to a carboxylic acid, you get carbon dioxide produced, and therefore you observe fizzing. So adding a metal carbonate, such as sodium carbonate or sodium hydrogen carbonate, will cause fizzing to a carboxylic acid, and that's how you can identify a carboxylic acid. Now we've just seen that carboxylic acids behave as typical acids in their reactions with alkalis, bases, metals, metal carbonates, and metal hydrogen carbonates. Now, the second type of reaction that they undergo is esterification. And esterification is the process of making esters. Now, esters have the general formula R, C double bond O, O, R. And R represents alkyl groups, and the alkyl groups in an ester can be the same or different. So to make an ester from a carboxylic acid, you heat your primary or secondary alcohol with a carboxylic acid in the presence of a catalyst which is concentrated sulfuric acid. Now an example of this is shown on this slide because I have ethanoic acid, a carboxylic acid, reacting with ethanol, an alcohol, to form ethyl ethanoate, an ester, and water, and the reaction is reversible. Now if we look closely at this equation, you can see that a hydrogen from the alcohol has joined with the OH from a carboxylic acid to form water, and the oxygen in the ester, the oxygen that's attached to the C double bond O, has come from the alcohol. Now the ester is called ethyl ethanoate because next to the oxygen in the ester, the oxygen bonded to the C double bond O, is a C2H5 group, an ethyl group. So that's why the ester's name starts with the ethyl, and the rest of the ester resembles ethanoic acid, so that's why the ester is called ethyl ethanoate. Now the concentrated sulfuric acid here has two roles. It acts as a catalyst and it acts as a dehydrating agent. And a dehydrating agent is essential to get a good yield of the ester. If you remove water from this system, the equilibrium shifts to the side that produces water, which is the right-hand side, and therefore this gives you a higher yield of ester. So the concentrated sulfuric acid has two roles. It acts as a catalyst, and its second role is to act as a dehydrating agent, which causes the equilibrium to shift to the right-hand side, the side that produces water, which gives you a higher yield of ester. Now the next reaction that we're going to look at of carboxylic acids is their reaction to form acid chlorides. Now acid chlorides have the general formula shown below. They have an R group attached to a C double bond O, Cl. And an example of an acid chloride is ethanoyl chloride, which is CH3 C double bond O, Cl. Now to convert a carboxylic acid to an acid chloride, you have to replace the OH in the carboxylic acid with a Cl. And to do this, you use a chlorinating agent. And there are a number of possible chlorinating agents that you could use. For example, one of them is phosphorus pentachloride, PCl5. And if you react the carboxylic acid with PCl5, you will get an acid chloride plus POCl3, which is called phosphorus trichloride oxide, and that is a liquid as well as the acid chloride, and you get hydrogen chloride gas. Now the problem with this method is you're making a liquid, the acid chloride, and one of your other products, POCl3, is also a liquid, so it can be difficult to separate the acid chloride from the POCl3, and this is because they can have similar boiling points. Now an alternative method is to use PCl3, and PCl3, phosphorus trichloride, will produce your acid chloride and phosphorus acid. However, that is not a preferred method because you can also have small amounts of phosphorus compounds being formed. So the preferred method tends to be to react the carboxylic acid with sulfur dichloride oxide, SOCl2, and that produces your acid chloride, which is a liquid, and two gases, sulfur dioxide and hydrogen chloride gas, and therefore you don't have the problem of separating the acid chloride from the other products because the acid chloride is a liquid and the other products are gases. So now let's test your understanding of how we make esters and acid chlorides from carboxylic acids with some practice questions. So here's our first set of practice questions. So read through the questions, pause the video, have a go at them, and then we'll go through the answers. Now question 1 is all about making esters, and you're asked to write word and chemical equations for the following reactions. Now when writing chemical equations, you can either draw full structural formula, where you draw all the bonds, or just structural formula. So I've chosen just to draw structural formula, and I'm not drawing all the bonds in. So propanoic acid and methanol make methyl propanoate and water. And propanoic acid is CH3CH2COOH, methanol is CH3OH, so you get CH3CH2COOCH3 plus H2O. And for B we have butanoic acid and ethanol, so we're going to get ethyl butanoate plus water, and butanoic acid is CH3CH2CH2COOH, ethanol is CH3CH2OH, and we're going to get CH3CH2CH2COO plus H2O. And for the last equation we have ethanoic acid and methanol, so we're going to get methyl ethanoate plus water, and ethanoic acid is CH3COOH, methanol is CH3OH, so we're going to get CH3COOCH3 plus H2O. So here's our second question for you to have a go at. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. Now for question 2, we have the ester ethyl ethanoate being prepared from ethanoic acid and ethanol in the presence of a catalyst of concentrated sulfuric acid. And the question is asking you to suggest one other use of sulfuric acid in this reaction other than a catalyst. Now sulfuric acid is a dehydrating agent, so if you remove water from this reaction, the equilibrium will shift to the side that produces water, which is the right hand side. So if the equilibrium shifts to the right, you get a greater yield of ester. Now for part B, you have to suggest one other method listing the reagents and conditions of making the ester ethyl ethanoate. Now the other way to make an ester is to have an acid chloride and an alcohol, and to make ethyl ethanoate you need an acid chloride with 2 carbons in, and that's called ethanoyl chloride, and it's a CH3 next to a C double bond O Cl. To make the ethyl part of the ester you need ethanol, and when you react an acid chloride and an alcohol together, you don't need a catalyst and you don't need to heat it up. So all you need to do is to mix the acid chloride and the alcohol together at room temperature to make this ester. So here's practice question 3 for you to have a go at. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So for question 3, you have to write chemical equations to describe the reactions of ethanoic acid and phosphorus pentachloride and propanoic acid and phosphorus pentachloride. So ethanoic acid is CH3COOH, phosphorus pentachloride is PCl5, and when you react them together, phosphorus pentachloride is a chlorinating agent and changes the OH to a Cl. So you get CH3COCl, which is ethanol chloride, and your other products are POCl3, phosphorus trichloride oxide, and hydrogen chloride gas, HCl. Now the equation for propanoic acid and phosphorus pentachloride is very similar. Propanoic acid is CH3CH2COOH. You react it with PCl5, so it's plus PCl5, and you get CH3CH2COCl, which is propanol chloride, plus POCl3, phosphorus trichloride oxide, and HCl, hydrogen chloride gas. So here's our 4th practice question for you to have a go at. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So for question 4, you're asked to write chemical equations to describe the reactions of ethanoic acid and sulfur dichloride oxide and propanoic acid and sulfur dichloride oxide. So if we do ethanoic acid and sulfur dichloride oxide first, we have CH3COOH plus SOCl2, and that makes CH3COCl plus SO2 plus HCl. And once again, the OH on the carboxylic acid has been replaced by a Cl. Now for B, we have propanoic acid and sulfur dichloride oxide. So we have CH3CH2COOH plus SOCl2, and that makes CH3CH2COCl plus SO2 plus HCl. And in both of these equations, we've changed our carboxylic acid to an acid chloride. And this method is better than the PCl5 method because the other products are gases, the acid chloride is a liquid, and it's easy to separate the acid chloride from the other products. Now the next reaction we're going to look at is reduction, and carboxylic acids can be reduced to form primary alcohols using a powerful reducing agent called lithium aluminium hydride, LiAlH4. And this is such a powerful reducing agent, you need to carry out the reaction in an inert solvent which is non-aqueous. And this is because the lithium aluminium hydride will reduce H plus ions in water to form hydrogen gas. So the solvent they use is a dry ether, such as diethyl ether, sometimes called epoxyethane. And this process is carried out by heating under reflux. Now you can see from this equation that the carboxylic acid changes to the primary alcohol, RCH2OH, and the hydrogen in brackets represents the hydrogen obtained from the reducing agent, which enables the reduction, a gain of hydrogen, to occur. Now you may remember that when you form a carboxylic acid, you can do this by oxidizing a primary alcohol. And if you partially oxidize it, you get another product called an aldehyde. So you might think that you can reduce a carboxylic acid to form an aldehyde. However, this doesn't work. If you reduce a carboxylic acid, it goes straight to the primary alcohol and doesn't stop at the aldehyde stage. Now it's also important to mention that this reaction does not occur with sodium borohydride that we've seen previously, because that is not powerful enough as a reducing agent to reduce the carboxylic acid. Now our last reaction is a decarboxylation reaction, and a decarboxylation reaction is basically removing a carbon and two oxygens from a carboxylic acid. Now carboxylic acids have RCOOH as their general formula. So if you remove the COO from this, you'll end up with RH, which is an alkane. And the alkane that you form has one less carbon in it than the original carboxylic acid. Now the way you carry out a decarboxylation reaction is to heat either the carboxylic acid or the sodium salt of the carboxylic acid with soda lime. Now soda lime is calcium oxide dissolved in sodium hydroxide solution. And these two equations show what would take place if you started with ethanoic acid and you reacted it with soda lime. So ethanoic acid is CH3COOH, and when you react it with NaOH from the soda lime, you get CH3COONA, so you get sodium ethanoate and water. And then this sodium ethanoate reacts with more sodium hydroxide to form your alkane, which has one less carbon in than the original carboxylic acid, and sodium carbonate. Now it doesn't matter if you start with the carboxylic acid or the salt of the carboxylic acid. If you heat either with soda lime, you'll end up with an alkane with one less carbon in it. And that's because the carboxylic acid will react with the sodium hydroxide from the soda lime to form the salt, and then this will react further with sodium hydroxide to form the alkane and sodium carbonate. Now the reaction is a decarboxylation because you're removing COO from the carboxylic acid. Now a common error with this reaction is that people believe that carbon dioxide is given out and is one of the products. It's not. The elements in carbon dioxide are removed, but the carbon and the two oxygens are taken up by the alkali to form sodium carbonate. So now let's test your understanding of this with some practice questions. So here's question 1. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So in question 1, we have benzoic acid being converted to phenylmethanol in a one-step reaction, and we're asked to name the reagents and conditions required for the reaction and to classify the type of reaction taking place. Now, to convert a carboxylic acid to a primary alcohol, you need lithium aluminium hydride. Now, this is also called lithium tetrahydroaluminate 3. Now, you get 1 mark for naming this reagent, and the conditions are reflux in dry ether as a solvent, and that gets you the 2nd mark. And the type of reaction taking place is a reduction, 1 mark for that. So here's our last practice question for you to have a go at. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So for question 2, you have to name the compounds formed from the decarboxylation of the following compounds. And the first compound is sodium butanoate. So if you decarboxylate this by heating it with soda lime, you will get an alkane with 1 less carbon. So you've got sodium butanoate, so the alkane with 1 less carbon will be propane. For the next one, we have sodium propanoate. So if we decarboxylate this, we get an alkane with 1 less carbon. So the alkane with 1 less carbon is ethane. For the next one, we have benzoic acid. We have a benzene ring attached to a C double bond OH. And if we remove the COO from this, we'll be left with benzene. And for D, we have a benzene ring attached to a CH2 and a C double bond OH. And if we remove the COO from this, we'll end up with methylbenzene. There's 1 mark for each of these. So that concludes this video lesson. So after watching this video, you should now be able to describe the chemical reactions that carboxylic acids have with alkalis, bases, metals, and metal carbonates. You should understand that carboxylic acids can be reduced to form primary alcohols and undergo decarboxylation reactions to form alkanes with 1 less carbon atom. And finally, you should be able to explain how carboxylic acids can be converted into acid chlorides and esters. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.